Okay, everyone. So it's our pleasure to have a second lecture by Francesco Maggi from University of Texas. And yeah, they will talk to us about soap films, and I'll let you talk.
All right. So thanks for the invitation to give a talk. And so this is a joint. The talk is based on a series of joint papers with Antonello Scardicchio, who is a physicist at ICTP, and with a graduate student at UT, Darren King, and with a postdoc student at UT, Salvatore Stuvard. So, and then we'll have a final slide that will tell you precisely which papers are related to this thing. So the starting point, okay, is the minimal surfaces model, which is the basic model for soap films hanging from a wire frame at mechanical equilibrium. Here you have in this picture taken in my office, you have a catenoidal neck hanging from some metal wire frame. And okay, so mathematically in this model, the wire frame becomes a closed curve. The soap film is modeled as a two-dimensional surface. The condition hanging from becomes the requirement that the boundary of your surface is equal to the closed curve W. And the requirement of mechanical equilibrium is expressed by the condition of the mean curvature of your surface to be equal to 0, which can be justified in various ways. So first way of justifying that is an argument called the balance of pressures. So essentially, you describe all the forces that act on an element of your surface, and then you prescribe their balance, because that's equilibrium. So in this case, one write down surface tension. So surface tension is the lateral pull of an element of surface that results in a net normal pressure on the surface. And this pressure is proportional to the mean curvature versus atmospheric pressure. And since the atmospheric pressure on the two sides of your surface is the same, essentially you're requiring in the model that the surface tension is equal to 0. So the pressure resulting from surface tension, more accurately, is equal to 0. So this is the argument of Laplace and Thomas Young, dating back to the beginning of the 1800s. And then, of course, there is a way of seeing this balance of pressures, the zero mean curvature condition, as a from the point of view of the principle of virtual works. This is a bit later by Gauss. So you consider the area of your surface S, and you deform your surface by, so it's the identity map, does nothing, plus a small parameter t times a displacement u times the normal to the surface. So you do a small normal deformation that doesn't move the boundary of your surface. So u is equal to 0 on w, on the boundary wire. And if you do the computation for this area increment, the derivative of t equals 0, you have the integral of the mean curvature times the displacement u. So if the mean curvature is equal to 0, then no matter what is the infinitesimal displacement, the change of area at first order is at 0. So that's why, and you recover the condition that comes from the balance of pressures. So what are the limitations of this model? There are several. So essentially the model, we are saying that whenever we see a soap film, we see a surface with zero mean curvature and prescribed boundary. So the first limitation as a physical model is of course non-uniqueness. So which of course it's very delicate, because it is not that in real life soap films appeared out of nowhere attached to boundary wires, right? So there is a dynamical process in dipping the wireframe and then taking it out that is partially responsible for non-uniqueness, but it's not completely responsible for non-uniqueness, meaning that there are some solutions of this mathematical model, some surfaces with zero mean curvature that you will never observe. For example, the classical example is the case where your boundary wireframe is given by two parallel circles at distance h of radius r. And mathematically speaking, when h over r is less than 1, essentially, you have at least 3 minimal surfaces, actually exactly 3 minimal surfaces. So you have either the two disks filling the two disks filling the two circles, and then you have two catenoids. Although you expect essentially to observe only the first and the second options, never the third option. This is called the unstable catenoid. So this is a surface mathematically, it has a non-trivial Jacobian value, which means down to earth, perturb it slightly and decrease the area. So whenever a subfield should happen to be into probably the two parallels. So an even more important reason, limitation of the model, is that it's that subfilms are smooth. A subfield that is quite common to observe. You see here, I've tried to create, I didn't get out of my experiment, or I get a line of singularities, and there is a floating disk of definitely it's not captured by a simple model. Using minimal surfaces films is that the model has no length scale. So if I just rescale my boundary wire, I have a circular wireframe of meters of diameter to
Francesco.
a huge wireframe.
Hi.
Yes.
Francesco, we're
Yes.
having trouble hearing you. You were losing your signal for the last 4 minutes.
Oh, okay.
I think it may help if you turn off your camera to preserve some of your bandwidth on your internet. That probably is the problem.
Okay. Okay. So that, should I go back a few slides?
I don't think you need to go back because we could see your slides well.
Okay.
Some of it
But-
too.
But Guy probably should be the person to judge.
No, not. But try at least to see whether when you speak now we can hear, right?
Okay. Can you hear me now?
Okay. Yes. So far.
Yes.
Okay. So I was talking about limitations of the minimal surface model, and another interesting one is that there is no length scale. So essentially, if you work with a circular wireframe and you just rescale the circular wireframe by a huge factor, according to the model, you still observe some subfilm flat disk filling it, right? So, which is of course absurd because we don't expect to observe a subfilm of arbitrarily large diameter. We expect that the thing will burst out, and simply because of, for example, a thickness that becomes too small, and then the chance of just random fluctuation making the subfilm disappear. So,
Francesco, I interrupt again. It seems to be fine.
Okay, thank you.
So sorry for your picture, but
no problem. You can hear me now.
Yeah.
Okay, good. Okay, so
sorry.
No problem. So, so the key points is that subfilms are actually 3D objects with a very small thickness, of course, but you cannot capture all their features, all their properties, just by idealizing them as surfaces. So that's the key point. So let me explain what should be the correct equations for subfilms in terms of a variant of the balance of pressures argument. So what happens if we do the balance of pressures argument, assuming that the film has a thickness rather than its a surface. And essentially the argument I'm describing, it's found in physics book. For example, here there is a reference in the book of Defay and Prigogine, although not with details, so it's just described with words, but let me try to explain what will happen. So let's say that we have a subfilm and we consider a sort of mid-surface, okay? And then our subfilm has a thickness, alpha of x, which changes as the point x inside the mid-surface is changed. So the subfilm will have two interfaces, a top interface and a bottom interface. which can be described as normal graphs of this thickness function. So x plus alpha normal and x minus alpha normal will give us the two actual boundaries of our subfield. The first thing we can do is write down the pressure on the subfield that is measured at the point x plus and x minus that are almost on the boundary of the subfield, let's say a bit in the inside of the subfield. So the pressure at the point x plus will be the atmospheric pressure P0 minus the Laplace pressure on the surface S plus. That is essentially a normal deformation of the mid-surface S by the thickness function alpha. And same thing for the pressure at x minus. You have to keep track of the signs, of course. There is an important constant here that you see, the surface tension, because of course the mean curvature has the dimensions of 1/meters, so you need some normalization. These are pressures, so are newtons over meter square. So you got the surface tension that has the units of Newton over meters. And then you can, assuming, for example, that this is a subfield that has formed into some gravity field, you have a difference of the pressure at x minus and x plus given by the vertical displacement multiplied by the density of the liquid solution and the gravity of Earth, if you are on Earth doing this thing, as it probably would be. So you just write down the position x plus and x minus, and you got a nice formula for this difference of pressures. And that's the system you have. So it's not that one now has a magical simplification, essentially. This is just the system we get. There is, however, something we can do to simplify it a bit. So let's, for example, write down the difference of the two pressures at x minus and at x plus using our formulas. So you get that this 2 rho g alpha vertical component of the normal is proportional to the difference of the two mean curvatures. Now, the two mean curvatures here can be written in the regime where, let's say, the gradient of alpha is small. So let us assume for a moment to be somewhere where the gradient of alpha is small. So this mean curvature can be approximately written as the sum of principal curvatures weighted by these 1/1 minus alpha ki and 1/1 plus alpha ki. So that when you do the Taylor expansion of these factors for alpha small, you get a cancellation of the first order term. So you get twice the mean curvature. The mean curvature is the sum of the principal curvature, plus something of order alpha square, which is also cubic in the, sorry, it's quadratic in the curvature. So this is the kind of equation we get. And you see, it doesn't say exactly that the mean curvature is at 0. It says that the mean curvature is at first order proportional to gravity. But even when gravity is absent, and that's very interesting, even when gravity is absent, the mean curvature is actually proportional to the square of the thickness, to this alpha square, that would be multiplied by something like cubic terms in the curvature. So you have a cancellation of the quadratic terms in the curvature. So this is very interesting because it tells you that even in an ideal situation without gravity, the mean curvature of the actual surfaces, of the actually boundary surfaces, should not be 0, should be close to be small, okay? Should be close to 0 and therefore be small and quadratic in the thickness of the field. So, which definitely is a way to think about subfields that reintroduces a length scale, because then you are prescribing the mean curvature to be equal to something. And then you cannot solve prescribed mean curvature on arbitrary large domains, for example. So this is just a balance of pressures, right? So let's summarize the equations in this left panel. And this is the mid-surface equation, that it's something you derive from this balance of pressures. But of course, you derive it in the regime where alpha is almost constant. And there are a lot of points that need clarifications in this argument. So for example, the first point is that we have introduced a length scale by using the thickness of the film, but actually thickness of the film is almost like making a strong kinematic assumption, let's say. We would like to work with a more fundamental parameter, with the volume of the film. And then there is the problem of having used the existence of a mid-surface, while there is no obvious mid-surface. For example, when you think about my catenoid with a singularity, so there is not a smooth mid-surface on which I can parameterize my minimal surface, in an obvious way, right? So what should one do of this derivation with this continuous normal vector field in situations where the normal vector field is actually not well defined, and these are physical situations? And finally, you may ask yourself, okay, but what is the variational framework? What is the principle of visual work that gives me the three equations in the upper left box? So can they be derived, at least in some situation, as Euler-Lagrange equation of some energy? So all these questions, to try to answer all these questions, we went back to the basic model. So the same energy that Gauss uses, because I mean, it cannot be a different energy, right? So we have to understand these balance of pressures in the context of capillarity theory. So that is just the perimeter minimization of a region under a volume constraint. So let me explain what I mean by capillarity theory. So in the typical problem in capillarity theory, we have a container, omega, and we have a region occupied by a liquid, so it's a region inside of omega. The volume of our region is denoted by epsilon. It's typically a small parameter, and the capillarity energy will be proportional to the area of, okay, here there is a typo. It should have been the boundary of V inside of omega, not the boundary of omega inside of V. So the first term here should be the boundary of the set E inside the container omega. That's the area you count. Then there is a coefficient beta that you use to weight the area of the boundary of V inside of the boundary of omega. So the solid liquid interface. So there is a liquid air interface, that is the first term. And then there is a solid liquid interface that is paid with a coefficient beta between -1 and 1, plus, if you want, the gravity potential. Okay, so in the case of subfilms, what would be the container, right? It's not, it's a very peculiar container, because the container of a subfilm is actually the complement of the wireframe. So think about your wireframe W as a delta neighborhood of a curve gamma. Okay, so it's kind of a solid tube. Gamma is a one-dimensional curve, but we have to understand it as a three-dimensional object now. So we take a delta neighborhood of this curve gamma. And then the container for our application of capillarity theory will be the complement of this solid curve. So our subfilms are constrained to live in the complement of this very peculiar container. And no surprise, if we minimize the capillarity energy at fixed volume in such a domain, we don't see a subfilm. We just see a little droplet of liquid sitting at a point of high curvature. So this is a result that is well expected, of course, and the mathematical proof is found in these papers that I have listed on the bottom right corner of the slide. So what to do? So you don't see, if you just plug in capillarity theory with the obvious choice of the container, you don't see anything that resembles a subfield, right? So how to progress? And we propose the following model, which is still based on capillarity theory, but somehow we are adding a spanning condition to it. So the idea is the following. Say that W is any compact set in Rn plus 1, but let's think about the solid neighborhood of a curve. And let's introduce something called C, a family of embeddings of S1. We just made a family of little rings that are contained in the complement of the wireframe. And our family C will be closed by homotopies. It means that as soon as I say, okay, this little loop is in C, then every other loop that is homotopic to my original loop and in the complement of W, so I can deform this loop into this other loop without ever crossing W, then also this other loop is in the family. So for example, I could take my loop and make it a bit larger. All my loops can be made bigger and smaller, right? So that I can make, for each point in between, I can make one of my loop pass through the point. And then by prescribing the intersection with each of these loops to be non-empty, I impose a spanning. So for example, here there is a version of area minimization under this condition. So we're minimizing the area of S. S is a surface, just a closed subset in omega, in the complement of the wireframe W, and we are requiring S to intersect gamma non-trivially for every gamma in the class of loops. Okay. So if this is not capillarity, there is no volume here. So we are in an n+1 and we minimize n-dimensional area. Okay. I will bring capillarity back in a moment. So this is just one possible formulation of plateau problem with this so-called homotopic spanning condition. Homotopic because there is an homotopic class of curves that you're using to generate the spanning. The existence of minimizers in this problem has been proved by, well, the condition itself has been introduced by Harrison and Pugh in 2013. And then there have been several papers, one by myself with Camillo De Lellis and Francesco Giraldin, then Guido has also worked on this problem and several other authors. So I've worked on this specific homotopic spanning condition. And let me also say that this is just one of the many options that people has been exploring in the last 10 or so years, even more, to produce formulations of plateau problem that can account for singularity in the minimizers. So we just focus on this one for the sake of definiteness, if you want. And let me give you an interesting problem of this property of this problem. So if you minimize n-dimensional area of an n-dimensional object in a n+1 under the condition of intersecting all these loops, then you can check that your minimizer, which exists, actually minimizes area, n-dimensional area, with respect to all Lipschitz deformations that are different from equal to the identity outside of the compact set away from the boundary wireframe. And these can be used using some old regularity theorems by Frederick Almgren and Gene Taylor, can be used to show that your minimizer satisfies the so-called plateau laws. So plateau laws, in the case of the planar minimizers, you may have singular points, but they come at from 120 degrees singularities, so 3 half lines meeting in a point. Or in higher dimension, essentially, you can see singularities, but they will be very simple, either Y points or T points. So Y points, it's really 3 half planes meeting along the line, and the C1 alpha deformations of this configuration. And T points is essentially you pick a point, you pick the regular tetrahedron around this point, and your surface will look like the 6 surfaces angular sector generated by this procedure, or a C1 alpha deformation of it. So this is the mathematical theory. So we have a very good plateau problem because it's compatible with singularity. So we can observe the singularities that are characteristic of subfields. And we have this homotopic spanning condition that can generate examples for us. So for example, simple examples are, let me just show them all in one shot. So if you have 2 points, this will be your gamma 1. And of course, you see a segment. If you have 3 points and you prescribe gamma 1 and gamma 2 and all the homotopic images, you will find a sort of triple point, Y point of this form. You can also have more complicated things. For example, 2 points with these just 2 curves, the minimizer is just going to be 2 lines. But as soon as you, for example, you also prescribe a curve spanning around these other 2 points, you will have possibly more complicated minimizers, right? Which may also lead to non-uniqueness. So for example, depending on the position of the 4 red points, 2 lines, 2 horizontal lines may have the same length of this configuration here that is connected. So it's a very rich structure. Essentially, my understanding of this model is that by prescribing the class C, it's like I am prescribing somehow what has happened after the dipping and taking out of the solution process, okay? So that's why I'm allowed then to see many different options for my minimizers. Okay, so this is the Harrison-Pugh formulation of plateau's problem. What are we going to do with that? We're going to make it into a capillarity problem. So to obtain a capillarity approximation of plateau problem. So we have our wireframe, which is a compact subset in Rn+1, so n is equal to 2 in the physical dimension. We have a spanning class, which is a family of homotopies of homotopic images of S1 in the complement of the wireframe. L denotes the infimum in the plateau problem. And we just use capillarity, with sigma equal to 1, no adhesion coefficient on the boundary walls, no gravity. Let's make it as simple as possible. We call it psi of epsilon, is the infimum of the area of the boundary of the liquid droplet in the complement of the wireframe. Our set will have volume epsilon, and the boundary of our set must intersect every curve in the homotopy class. So this is schematics. So W is this green thing. I have just drawn a couple of curves in the class C. They're all homotopic one to the other. And the minimizer E, it seems a surface in this picture. This other picture is better, a sort of mid-section picture. You see that E is a three-dimensional object, but you see, it cannot be a droplet, because if it would be a droplet, eventually it will not intersect some of my curves. So it needs to stretch out. The boundary of E needs to stretch out across the curve to realize the spanning. And it's a three-dimensional object because it has positive volume. Of course, this is a very degenerate variational problem, because what could go wrong? A lot of things. So if you take, for example, a minimizing sequence, J, so a sequence of sets was areas here was perimeters, goes to the infimum in the problem, these sets may very well decide to collapse somewhere. You see, the EJ here has positive volume, is a open set, let's say, but then as it converges just in volume to a limit set, somewhere the two faces, the two bounding surface, collapse one onto the other and give you twice the area. And there is nothing forbidding this to happen. So if this will be energetically convenient, the model will try to do that, okay? And we're going to see in a moment, this is indeed going to happen. So the first theorem that we have is the best general result you can get. There will be minimizers in your problem, but they will, in this capillarity version of plateau problem, but they will only be generalized minimizers. So, so let us assume that the infimum in the plateau problem is finite, that the boundary of the wireframe is smooth, and that the complement of the wireframe, even if we enlarge it a little bit, it's connected. So these are kind of extremely basic assumptions to be sure to get some geometry that is not completely foolish. Then every minimizing sequence in this capillarity problem psi of epsilon at volume epsilon will admit a limit, which is not just a set. You don't just get that EJ converges to a set. The limiting behavior of EJ will be described rather by a pair, kappa and E. So E will be indeed a set with the right volume, with volume epsilon, but the boundary of E will be contained into a larger set K, and it is the set K that will realize the spanning condition. So it's like the EJs converge in volume to a limit set E, but this limit set E, the boundary of this limit set E will not be able to touch all the curves in the spanning class. This will be achieved only by a larger set K. So let me see if I have on this slide. Let me just go quickly, okay, to this slide, then I will come back. So you can see here that my minimizing sequence, so S would be the minimizer in the plateau problem for these three disks, okay? And my minimizing sequence will try to converge there, but somewhere it will collapse. You see here on these purple regions, this is the part of this compact set kappa minus the boundary of E. Here it will collapse with multiplicity 2 to achieve the spanning condition. And the limit set E has the right volume, but just sits in the middle of the picture, okay? So let me go back one slide and describe the convergence. So you can see here in a bit of technical terms, so the areas, the boundaries of this minimizing sequence will converge to the boundary of the limit set E with multiplicity 1, and then with multiplicity exactly 2 to the part of this compact set outside of the boundary of E. So the total energy of the problem, the optimal energy, will be twice the area of the collapse part plus, with multiplicity 1, the area of the limiting set. So we get a standard minimizer if the collapse, if this set K is just given by the boundary of the limiting set. We will get a collapse minimizer if the area of kappa minus the boundary of the set will be positive, which is
Francesco.
yes.
Are we to think of E as being maybe it's the closure of its open interior, or it's an open set? I mean, in other words, it does have an open representative.
Exactly. E is an open set. So when I'm writing boundary, you can really think about the topological boundary.
Okay.
I have already cleaned up the set so that you don't see fake boundary points, like I'm adding somewhere something.
Yeah, okay, all right.
Related,
so
okay?
E is open, fine. That's
yeah, I have already done all the job of, you can think about really simple natural terms to the problem, okay? I'm trying to be not too much technical because this is actually very technical, as you can expect. Okay, so let me go to this next slide. Let me just see the whole slide. So here you see there are two examples. Say that W was given in the plane by two disks. So the minimizer in the plateau problem S will just be a segment. Was length equal to L is just the distance between the two disks. Very simple. What is the minimizer in my problem? Well, the minimizer in my problem will be given by two circular arcs of very small curvature. So the curvature will be proportional to the volume constraint. The optimal energy will be twice the length of the plateau minimizer plus some constant epsilon square plus little o epsilon square. So this will be the graph for epsilon small of the capillarity approximation of the plateau problem. While plateau problem will just see this 12. While if I have 3 disks, you will see that, okay, the plateau minimizer will be a y point. The minimizer in the epsilon capillarity problem will be a small triangular region with negative curvature enclosing the volume epsilon, and then as a memory of the spanning condition you imposed, you will see these collapse segments that indeed make K contains the boundary of V, it's larger than the boundary of V, will allow K to realize the spanning condition. So let me show you an interesting fact. So what is the psi of epsilon in the case of 2 disks? We said it's quadratic for small volume, and then for large volume, it has this isoperimetric behavior in the plane, square root of epsilon. But what happens in these, in the case of 3 disks, it happens that the circular arcs here will have curvature, negative curvature, huge negative curvature of order 1 over square root of epsilon, negative that, which means essentially that the optimal energy functional will be lower than the plateau energy for small volume. It grows like 2L minus constant square root of epsilon. And then eventually it will behave in an isoperimetric way. So this tells you something very delicate. This tells you why this problem is difficult, because you see, if there is a singularity in the limiting plateau problem, then the behavior of the energy functional is completely opposite. Here I have very tamed surfaces whose mean curvature goes to 0, and that can be expressed as graphs, normal deformations over a limiting plateau surface. But as soon as the plateau surface, the limit plateau surface has a singularity, I see negative curvatures, unbounded. So this thing will have bounded, the sequence of minimizers here will have bounded curvatures only in L1. But why in L1? Because you have a balance between the domain of integration and the size of the mean curvature. So it's very delicate. There is almost no compactness in the problem. And that's why the proofs to get these things done are so delicate. So the next theorem I want to tell you about is a general theorem that tells you that under the same assumption of the existence theorem, the optimal value function psi of epsilon is lower semi-continuous, grows in an isoperimetric way at infinity, but most important of all, converges to twice the energy in plateau problem as the volume goes to 0. So that's a very important theorem for us, because it's telling us that by introducing this capillarity approximation, it's not like we're introducing something that in certain situations for epsilon small, it's entirely different from plateau problem. Actually, if you take a sequence of generalized minimizers corresponding to volumes going to 0, then there always exists a minimizer in the plateau problem such that in energy you converge there. So twice the energy of the area of the collapse region plus the area of the non-collapse boundary converge to twice the area of the plateau of a limiting plateau surface. So what is the conjecture that you can make based on these few examples? That in the case where every minimizer of the plateau problem is smooth, so in a case where I give you some boundary conditions so that minimizers S in plateau problem are smooth, they never have singularities, then I may hope that I converge there smoothly so that my boundaries, my capillarity boundaries, never have this collapsing, okay? Never have this complicated structure, but just look like normal graphs. So this is the conjecture we are working on. So the fact that whenever the limiting plateau problem has not singular minimizers, then the collapsing can be excluded in the capillarity approximation. Moreover, this convergence happens with a sort of selection principle. So I won't enter into details, but the minimizers in the capillarity problem will always choose the limiting plateau surfaces that have more curvature or that have more singularities, okay? So if more singularities, for example, if you are in the plane and you have two minimizers in plateau problem, one with 4 singular points and one with 6 singular points, okay? The minimizer in the psi epsilon problem will prefer to converge the one with 6 singular points because these allow them to lower the energy even further. So what's next? What's next is a basic regularity theorem. My existence theorem, when I say that there exists a generalized minimizer, these sets K, this pair KE can be very, very bad, okay? Can be sort of generalized notion of surface, would just be rectifiable sets in technical terms. So what we can show is that if you look at the limit energy, that is twice the area of the collapsed part plus once the area of the non-collapsed part, then our generalized minimizer minimizes this limit energy with respect to all diffeomorphic images that preserve the volume, okay? This is the first information because in principle, we don't know anything like that because since this is just a generalized minimizer, it's a minimizer in the sense that it has energy less than what can be achieved by a minimizing sequence. But the question is, okay, can every diffeomorphic image of a generalized minimizer be achieved by a minimizing sequence? Okay, the answer is yes, and this theorem gives you then the minimality inequality. And what you can deduce from this minimality inequality is that there will be indeed a singular set contained in K with the following property. Okay, so if you look at the part of K that is outside of the singular set and outside of the boundary of E, this will essentially, this purple part in this drawing, this will be a infinity minimal surface. So it has zero mean curvature and will be smooth. Then there will be a regular part inside of the boundary of E, denoted with this little star. For the specialist, this is the reduced boundary of E as a set of finite perimeter, which will be a constant mean curvature surface. So this blue part here will have constant mean curvature. So in this problem, you have a transition from 0 to constant mean curvature. So there is a free boundary that is this boundary of E minus the reduced boundary of E, about which we just know it has empty interior. So we know very little, okay? For the moment, we just know it has empty interior. While, okay, apart from this transition region from constant to zero mean curvature, otherwise, the singular set is known to have zero area. Okay, this is the basic regularity that you get from this information of minimizing the relaxed energy, the limit energy, with respect to every diffeomorphic image. But you can do better. So let me explain in the next slide the results contained in a recent preprint where we show that the singulars outside of the closure of the wetted region, okay? So in the collapsed region, the singular set is actually empty in all the physical dimensions, for example. So let me explain this. So take a generalized minimizer and now take a deformation that it's different, but that it's supported as a deformation away from the closure of the wetted region E, okay? So I am deforming my, my collapse region in a way that I don't touch, I don't move the part that encloses the volume epsilon, the part E, okay? Then we can show that all such images can be approximated by sequences in the competition class, and therefore that KE minimizes the energy along these deformations. This is very technical, very delicate to show, but once you've shown it, what you do know? For example, in the case n equal 2, well, you know that the collapse region, so the part of kappa outside of the closure of E, okay, is a minimizer of the area with respect to Lipschitz deformation. Therefore, its singular set contains only Y and T points by the theory of Almgren and Taylor I was mentioning before. So this is a huge improvement, because what we were getting before was just that the singular set at 0 area. Now I'm telling you, no, the singular set may have finite length, but it will be locally diffeomorphic either to the cone Y or to the cone T. And then we can do even better, because we can say, but let's try to say that we have this situation, right? The collapse region K has a Y point, like I've been drawing here, and this is the wetted region E. But I can show by using what we call wetting competitors near Y points that no Y points can exist. Why? Because if I have a Y point, you see, as in this picture, I can do a competitor. I have to show that this competitor, I can work with it, because this is not a Lipschitz deformation for sure. But you see, I can create a competitor where at the scale rho, I somehow cut, I save area, rather than paying the Y point with multiplicity 2, I just add to E a wetted region around here, and then I restore the volume constraint by pushing somewhere else. So by doing this competitor, I gain area order rho to the n at a cost to restore the volume of order rho to the n plus 1. So this is advantage. This is a good competitor, and it excludes the existence of Y points. And if you don't have Y points, you cannot have T points too. So as a consequence of this combination, let's say, of showing that Lipschitz images outside of the wetted region are admissible, and then variational argument, you can eventually prove, as we did in this second paper, that in the physical case, the collapse region is actually smooth. In all the physical cases, the collapse region do not have singularities, which in a sense, it's telling you a strong indication, something we would like to prove, that, let me go back to this slide. You see here you have a small volume epsilon. We're saying that kappa minus boundary of E, as in this picture, is irregular. So our conjecture now is pretty clear that if S is a minimizer in the limiting plateau problem, okay, the singularities in the limiting plateau problem cannot be accessed by the collapse region. It's always the wetted region that converges there. And somehow the collapse region will be a smooth normal graph on the smooth part of the limit minimizers in the plateau problem. This is all to be proved, but we have strong indication of this behavior at this point, thanks to this regularity theorem for the collapse region. Again, in this spirit, so exploiting local deformations that are not, they don't come as Lipschitz images, we can prove some other interesting theorems. The next one is the following property. So when we can show that whenever there is a collapse region outside of the closure of the wetted region, then the constant mean curvature of the wetted region is negative. So, so you see in this picture that I had here, you see I'm always drawing, when there is a collapse region, I'm always drawing the region E with negative curvature. This is not just, I could have drawn it like a bubble, like a round bubble. Instead, it's drawn like a sort of concave bubble. Why? Because that's the only possibility. That's what is proven in this theorem. As soon as there is a non-trivial collapse region outside of the wetted part, then the constant mean curvature must be negative. That's what is proven in this theorem. And using this property of negative mean curvature, we can show that the collapse region is containing the convex hull of the wireframe. Okay? So the proof is again obtained by some competitors that are not Lipschitz images. So specifically see here, I have the collapse region with multiplicity 2. And the kind of competitor we do is like we open up this multiplicity 2 region into 2 multiplicity 1 regions, and then we recover the volume somewhere else. And because we are adding volume, so we have to decrease volume somewhere else in the wetted part. And if you do your computation, this is, if E has positive curvature, as in this picture, then you have a gain in energy. So that's impossible for a minimizer. So that's why for minimizers, this lambda must be negative. Okay, this is just explaining that this is convenient in area. So these are the papers where all these theories contained. So the first paper is in collaboration with Antonello Scardicchio and Salvatore Stuvard. This is the paper where we introduced this balance of pressure, and where we introduced this capillarity model, and we study limits of surfaces with vanishing curvature. Then in the paper with my student Darren King and Stuvard, which appeared on Communication in Pure and Applied Mathematics, is the paper where we build the existence theory and the basic regularity theory. And then there are these other 2 papers. In the third one, we prove the smoothness of the collapse region. And in the first one, we prove this negativity of the Euler-Lagrange multiplier and the convex hull property. So I think that I have used my time. So I will thank you and stop here.
Okay, thanks a lot. Yeah, I try not to make it. That was beautiful. So let's say, anyone has questions? Go ahead. So
there's a question in the chat.
Okay.
Craig.
Question in the chat.
Okay. Why did so the question is, why is there not a wetting condition between the film volume and the tube it is attached to? For example, is it, yes, absolutely. So this is just so thanks for the question. It's a very natural one. I agree with you. And this is not included in the model so far, just for the sake of simplicity. So when okay, let me see if I can go back a few slides. But I totally agree with you. When I formulate the model here, psi epsilon, I just keep the main term in the capillarity energy, and I'm setting beta equal to 0. But this is not because beta different from 0 wouldn't be interesting. So you could definitely have beta of all the range from -1 to 1. And if you think about this example here, for example, this is my example where beta is equal to 0. So nearby the circles here, I expect to have a 90-degree condition, right? But what happens if I put different values of beta? For example, beta negative. Well, what I expect to see when beta is negative is that I will leave the wireframe more and more tangentially. And I think that when beta is negative, even with 2 boundary circles, you may have collapsing, meaning that for beta sufficiently negative, the minimizer should just start with negative curvature, just do all the wetting near the wireframe, and then being collapsed in the middle. So that's what I expect. So I have essentially, I gave to a student the very delicate task of reproving this existence of generalized minimizers and re-understand what we've done so far with this beta non-zero. But I would expect that for beta different from 0, even in simple situation like this one, you will see wetting and collapsing. Wetting near the boundary wire and collapsing in the middle of the domain. I hope I have answered the question somehow. Okay. Yes, well, it's not an assumption. I mean, that's the conjecture, I would say, that in the theorems that the fluid collects in regions of high curvature. Yeah, more than an assumption, that's what we would like to show, you know, that rigorously. So we would like to show that if you consider the plateau problem, the one for surfaces, and say that you observe, for example, a unique minimizer that has singularities, okay? So what we expect as a consequence of what we have proved, but with additional work, we are not there yet at the level of formal proofs. What we expect is that if you take a sequence of minimizers in the capillarity model with volume going to 0, then all the volume will be concentrated upon the singularities and you will have collapsing everywhere else. So that's the kind of generic behavior we would like to describe and that we expect.
Okay, what do people think? Can you wet a Simon's cone? Do you?
Okay, so yes. So let me go back to my theorem, to this improved regularity theorem, let's say, because there was a basic one, right? So the basic regularity theorem for the specialist was this one. This is just showing that diffeos are admissible and then saying, okay, then I have a varifold that has bounded mean curvature and therefore I can apply Allard, okay? This is the basic, how you get the basic regularity. But in this theorem, the regularity of the collapse regions, where we do this much more refined analysis because we prove that Lipschitz maps are admissible. So the fact that Lipschitz competitors for the collapse regions are admissible tells me that I have only y-nt points in dimension 2, but actually in arbitrary dimension, it tells me that the top strata of the singular set are given by y-nt points cross copies of Rn with the right dimension. So actually, once we have excluded y points, we can exclude also t points. And so we deduce that the singular set has dimension n minus 3. Therefore, we can apply the Schoen-Simon regularity theory and check that the singular set has codimension 8. So in particular, the only singularities for the collapse region will be observable in dimension 8, in ambient dimension 8. Of course, we don't care about them too much because our motivation is very physical. But in principle, the collapse region in dimension 8 may have, may consist of a Simon's cone, okay? And then, yes, I would definitely expect that minimizers in the capillarity problem would decide to put, if not all, 99%, an increasing percentage of their volume near the singular point. But this is just based on the analogy with these lower dimensional examples. So it's a question that would definitely require more thinking, okay? Mm-hmm. Because it's just given in analogy. So it could be that actually for the Simon's cone, it's smarter to put the liquid, to distribute the liquid with a normal deformation around the smooth part, as in this picture, right? And then somehow near the singular point, you decide to do nothing. I don't believe that because, I mean, heuristic computation shows that you want to converge the minimizer with more curvature.
Yeah, but I don't know how to compute the curvature of Simon's cone at the origin, right? Is it positive, negative? What is it? Yeah, you know, it's a mess. But
well, the curvature, I'm sorry, the curvature I really mean, well, you know how the curvature scales, right? You know that it blows up as the inverse distance from the origin. So it's definitely becoming larger, which is why if you do a formal Taylor expansions of the area of these objects of a two-sided neighborhood somehow, it would suggest that you like to go there. But of course, I don't have a two-sided neighborhood until the singular point. So that's why it's not completely clear what I'm really saying here, right?
No, that's what I was asking. Okay, other questions? Now that time at people to think.
Can I make a question?
Hmm?
So I have a question.
Go ahead.
Oh, okay. No, as far as I understood, you conjectured that if there is a limiting smooth minimal surface, I mean, if the only solution of the Plateau problem is a smooth minimal surface, then actually you always have some thickness around it. So there is no collapsing, right?
Yes.
So have you tried something in the situation in which, I don't know, the smooth minimal surface is a plane, for instance? Like then,
so
or at least, with, I mean, if you set the problem among graphs, if you're already imaging that, collapsing region is going to be, so the boundary of your minimizer is like two graphs. So like in the heuristic model you were describing at the beginning. So can you say
so
that thing? Or?
So in the case that you have, say, a planar convex domain, and you prescribe the boundary data like a smooth curve over this smooth convex domain, over the boundary of the smooth convex domain, we can show that there exists only one minimizer in the Harrison-Pugh model that is given by solving the classical minimal surfaces equation. And then we have a very long heuristic argument that we would need to flesh out to the details, okay? Showing that showing that a sequence of capillarity minimizers with volume going to 0 will have non-negative curvature, and then we'll have a bound from above on their mean curvature. And this essentially gives you the ability of applying Allard theorem and show smooth convergence of our minimizers towards the limit surface. Now, this is not yet a theorem. That's why this is not yet a theorem, in the sense that I've just described you a sketch of proof somehow, very, very vaguely, okay? But there are a lot of technical points that needs to be clarified. So I definitely expect we will be able to answer this conjecture in the case of where the plateau problem is the plateau problem corresponding to a convex set and the graph over the function of the boundary of a convex set. In that case, we should be able to answer this conjecture affirmatively by these arguments that right now we don't have in formal, at a formal level of accuracy. But more in general, it seems difficult because of course, I mean, how do you know, I mean, it's not really an easy property to exploit. So what does it mean that as an assumption for a theorem, right, that the plateau problem has only smooth minimizers? So it's not so obvious to me how to attack the general conjecture. But I agree with you. I mean, the main example where you expect minimizers in the plateau problem to be smooth is the graph-like case. That's the example where you expect to be able to show something like that. And in that example, we have at least a heuristic argument to build a rigorous proof.
But can you add some sort of smooth convergence, say in low dimension of the, I mean, somehow you can think this.
Yes, exactly, with smooth convergence. So the idea would be the heuristic argument, the idea of the heuristic argument would be showing bounds on the mean curvature, like not like a bound like it's going to 0, like a bound like it's universally bounded in terms of the data of the problem, which then would imply smooth convergence and therefore the fact that the mean curvature is going to 0. The mean curvatures of the approximating capillarity surfaces. So we would, in a sense, in this case of graphs, we should eventually be able to justify this Laplace pressure argument here.
So
okay.
For the linearized problem, at least as long as there are small deformation of a graph, you know the conjecture to be true.
Yes. For example, if you start, another thing that should be easy to prove, I mean, I've never tried to written it down formally, I just have sketched it on a piece of paper, but another thing that seems very provable is that if you start from some minimal surface, which is strictly stable, okay, and smooth, then you should always be able to construct a critical point of my capillarity energy. Okay, so at least locally, you should be able to move it and find and sandwich it between two constant mean curvature objects, if the mean curvature is sufficiently small. So, but this of course it's hard to tie this result to the global minimization in the generic case. So that's why this case of graphs seems more approachable and in a sense interesting, because anyway, I mean, it's something that you see a lot in applications, right? So that the graph-like structure.
Yeah, at posteriori.
Posteriori.
Okay, guys, I'm supposed to be the mean guy. Francesco, you'll be still around. There's a session for you, right?